I am a technology analyst at IEAGHG, and it's my pleasure to welcome you all to this webinar. We're going to speak about steel, decarbonization of steel production from a techno-economic and life cycle assessment perspective. So why is steel important? Steel is a critical material in modern infrastructure and manufacturing, used in pretty much everything from buildings to transportation to machinery and consumer goods. It is a critical component to global industries and economies. And why is the decarbonization of steel important? Steel industry is one of the largest industrial emitters of CO2, and as such, reducing its carbon footprint is essential for achieving global climate goals. I'm going to share my screen. Okay, very well. You can all see my screen, isn't it, Sylvian?
Yes, it's not in presentation mode at the moment, but yes, we can see it.
Fantastic. Very well then. So against this backdrop, the IEAGHG commissioned ERM to conduct a study on pathways to decarbonize the production of steel. So who are we? The IEAGHG is a technology collaboration program, and we're part of the International Energy Agency's technology network. We are functionally and legally autonomous, therefore views, findings, and publications of the IEAGHG do not necessarily represent the views or policies of the IEA. IEAGHG has made an extraordinary contribution to advancing CCS over the last 30 years, and that's all down to our members. Our membership is at the center of everything that we do, and thanks to our members for their support and for steering the course of our activities. For the sake of time, I'm unable to go throughout the activities in detail, but IEAGHG, we are at the forefront of carbon capture, utilization, and storage research. We advance technology that reduces carbon emissions and accelerate the deployment of CCUS and carbon dioxide removal projects worldwide. We have a broad spectrum of publications that you can access on our website on topics including capture, transport, storage, monitoring, regulations, and more. IEAGHG hosts two of the world's leading CCUS conference series, the Greenhouse Gas Control Technology series, as well as the Post-Combustion Carbon Capture Conference series. We are also the organizers of the International CCS Summer School, an incredible opportunity for early career researchers as well as postgraduate research students. The next GHGT conference is the GHGT 17, and join us at the world's leading CCS conference. This event will bring together researchers, industry leaders, government officials from all across the world to explore cutting-edge technology, innovation, and greenhouse gas mitigation strategies. The IEAGHG Clean Steel study was conducted by ERM, and I wish to acknowledge the study authors, Sylvian Baltag, Anisha Harris, Ignacio Rapsion, Sebastian Hay, Yemini Panchak-Shoram, Tom Butler, Jacob Jones, and Charlie Ridman. The study objectives are as follows. The Clean Steel study presents a comparative analysis of steelmaking pathways, taking a techno-economic and life cycle emissions perspective, gain insights into the primary energy and infrastructure implications associated with large-scale deployment of different steel decarbonisation pathways, to estimate the price premium that clean steel could command, and formulate recommendations for key stakeholders to support the sector, and outlines recommendations for future work. I will be moderating this discussion, and we will be hearing from Sylvian Baltak as well as Ignacio Rebion. This webinar will last for about 60 minutes, and as such, there will be no coffee break. There is going to be Q&A sessions in the last leg of the webinar, and I encourage you to post your questions and keep yourself engaged in our discussions. This webinar is going to be recorded and hosted on the IEAGHG's website in the coming days. So let's get started. It's now my pleasure to invite Sylvian, who will give context for the discussions that will transpire in the coming hour. Sylvian.
Okay, thank you, Abdulaziz, and good afternoon, everyone. Very pleased to be here. I think our slides are coming on. So I'm Sylvian Baltak. I'm one of the partners at ERM, and my focus is on industrial decarbonization and CCUS. So who is ERM? I'll say a few words about us, and then I'll tell you a little bit more about the study, what we've done, and then pass to Ignacio to go into the details. So in case you're not familiar with ERM, we are the largest pure play sustainability consultancy in the world, around 8,000 people globally, 40 countries. We have been around for around 50 years, and we are working in many of the countries globally. We advise clients on all aspects of sustainability, all the way from corporate reporting to GHG inventories, all the way to climate change strategies, to industrial decarbonization strategies, to Techno-Economic studies on CCUS, hydrogen, blue ammonia, sustainable fuels, all the way to implementation of projects through permitting, consenting, capital project delivery, social license to operate, and so on. We are not an engineering firm, so we don't do EPC studies, but we focus on all the other aspects of project development. Perhaps a little bit about our work on the CCUS space. So there you go, the slides are coming, and I'm not going to go through each one of the items here, but as you know, CCUS and industrial decarbonization are a very complex topic. There are many aspects that need to be considered as the industry develops, and I think we are proud to say that we cover many of those aspects, and we have been working with our clients in many industrial clusters and hubs and across the world to understand the commercial feasibility of different CCS projects, to understand how you gather emissions, which technologies are suitable, to understand the business case and the financing of different projects, the capital requirements, the subsidies and incentives that might be needed, how you deliver the projects in terms of capital, project feasibility, construction, permitting, and so on. We help companies mitigate some of their social risks when it comes to CCS projects. We know that stakeholder engagement is a key part of this, as well as ensuring that there's a just transition for the industrial regions. And of course, we support clients understanding the carbon competitiveness, the life cycle assessments, and the impacts of the different technologies. And that's exactly what we've done for the Clean Steel project. So on the next slide, I'll just introduce you to what the focus of this project was. And it's worth to say that we started this work almost 2 years ago, and the study went on for, I would say, 9 to 12 months. And it was a very iterative process and quite expansive. So the aim of the study, as Abdulaziz mentioned, was to understand the different technologies required for decarbonization of steel. Some of those technologies are nascent, so we are trying to understand what is their technology readiness, what will be their techno-economics, so when are they available, how much they're going to cost, which parts of the iron and steel value chain they're applicable to, what sort of emissions they could be reduced, are they applicable to a blast furnace, are they applicable to a basic oxygen furnace, can they be linked to other emerging projects in infrastructure that are emerging around hydrogen, carbon capture, and so on. we try to also understand the life cycle assessment. So we know that steelmaking is a very energy-intensive process, and actually, indeed, it kind of represents around 7% of the global CO2 emissions. So this is a very intensive and large sector. So understanding how those technologies could help reduce the carbon footprint is very important. So we not only did techno-economic analysis, but we also conducted life cycle assessments, LCAs, of the different pathways. So at the end of the study, and Ignace will be talking through the findings in a second, we looked at all the pathways that we feel like would be upcoming in terms of steel decarbonization, consider their costs, consider their life cycle assessment, and started to think about what this means in terms of infrastructure, in terms of primary energy consumption, and also what would be the impact on the price of steel. Because let's face it, decarbonization and CCS and hydrogen technologies are more expensive than emitting the carbon today without a proper carbon price. So understanding what would that mean in terms of additional costs to the producers and to the customers of the steel is important. And we do know that there's a market for green steel emerging at the moment. So we were trying to understand how those technologies could help accelerate that market, and which market segments might be more likely to purchase the clean steel that will be produced today or in the future with those technologies. So without further ado, I would like to pass over to Ignacio, who will be talking through some of the findings. And of course, we're happy to take any questions at the end. Please put them in the chat. We have a Q&A discussion, and of course, our emails are also available at the end of the presentation in case you want to contact us offline and discuss this further. Thank you.
Thank you, Silvian. Great. So we can now dive into the findings and what emerged, what were the results from this study. But before going straight into that, I wanted to talk a bit just about the scope. Steel can be done via two main production pathways or routes. Those are the primary route, where iron ore is the main input, and the secondary route, where scrap steel is the main input. There is a huge role for secondary production in decarbonization because it has a much lower energy and CO2 intensity. But the issue is that the growth of secondary production is constrained by the availability of scrap, and more scrap will become available only with time. So decarbonizing primary production is an imperative, and that's why this report focuses on the decarbonization of primary production. We are not touching on the alternatives for secondary steel production decarbonization that are more related to the procurement of renewable electricity. In terms of primary production, there are two main pathways that are commercial and that are used today. One is basic oxygen steelmaking. That's the one that dominates and represents about 90% of total primary steel production. The other one is the direct reduction of iron using natural gas-based process. That one is significantly smaller in terms of production volumes. That said, we built on these two main production pathways. You can see the BF-BOF, that's basic oxygen steelmaking, on the first row, and natural gas-based DRI plus an electric arc furnace where direct reduced iron is melted. We built on those commercially available and mature pathways to develop which are the emerging pathways that modify each of those technologies. In total, we modeled 9 production pathways. These are not totally exhaustive of the possibilities that the steel industry has to decarbonize, and there are examples of other pathways that are being considered and are under development. But in terms of basic oxygen steelmaking, other than the conventional unabated pathway, we considered retrofitting carbon capture and storage to the blast furnace, combined with a modification of the blast furnace with top gas recycling to become an oxy blast furnace. The same pathway, but where charcoal is used to replace pulverized coal injection into the blast furnace, and then a pathway where hydrogen is injected into the blast furnace. For each of these, we model the complete mass and energy balance where for example, the amount of hydrogen that is injected into the blast furnace is constrained in terms of the energy balance, the fact that from a metallurgy or process engineering point of view, hydrogen reduction is endothermic, so you can only inject a certain amount. The rest has to be with coke or pulverized coal injection and other considerations of that sort. In terms of the direct reduction routes, other than the unabated and conventional natural gas-based pathway, we looked at CCS, where CO2 from the flue gas stream from the gas reformer from the direct reduction plant is captured. And then we looked at 2 hydrogen pathways. Both pathways represented a 100% hydrogen-based direct reduction. That is, there are many combinations of hydrogen and natural gas plants that are being proposed and studied, and many incumbents are planning to build gas-based direct reduction facilities with a gradual transition to hydrogen. In this case, we modeled 100% hydrogen use. One of those pathways also is combined with the use of biocarbon in the electric arc furnace. So carbon is typically added to the electric arc furnaces for improved energy efficiency, to generate some foam in the slag that improves the refining of the metal, and some process parameters that I don't want to delve into those details, but the coal that is typically used, or the fossil carbon that is typically used in the electric arc furnace, in this case, we assume that it's being replaced with biocarbon. And the final pathway is one where after the natural gas-based direct reduced iron, there is an intermediary step where there is an electric smelting furnace. This is a pathway that is being considered by some steel makers because it allows for the continued use of lower grade pellets. Direct reduction pathways typically require a DR grade pellet that is higher quality and represents a very small share of total merchant iron. So to address that limitation, we included this pathway here. There are others, as I mentioned, that are not included here, as blends of hydrogen and natural gas, the use of that electric smelting furnace pathway with hydrogen, electrolytic pathways that are under development. Great. I've been a bit technical so far, so let's dive into the results. That will be a bit more fun to look at rather than this very dry description of pathways. So what we found first in terms of costs is that unabated basic oxygen steelmaking results in the lowest levelized cost of production across all pathways. And that's the reality today with the effective carbon prices. In all cases, what we have been modeling is the production costs for a steel mill in Northern Europe. So the representative electricity costs, the grid intensity of electricity, and the carbon prices are representative of Northern Europe. And what we calculated here and what we are showing in the chart on the left-hand side are the levelized cost of production. That means they take into account an annualized capex, assuming that an existing steel mill is reaching its end of life and is facing a critical decision about, hey, do we extend the lifetime of this blast furnace by relining it and potentially doing some retrofits, or do we move towards another pathway like direct reduction of iron? So the capital costs that are here are not those of developing a greenfield steel mill, but adapting a brownfield steel mill. As you can see, the capex costs, when they are annualized, represent a very small share of the levelized costs of production. Whilst government funding or capital grants can play a very important role in unlocking the access to capital that can be problematic, in terms of the levelized cost of production, they don't ease the pressure much on steel mills. And you can see that the big increase in production costs would come from access to energy and reductants. So that means access to, let's say, biochar, access to biomass or access to hydrogen in the case of the hydrogen pathways. There is a modification in terms of carbon price. You can see that in the chart, the difference between where the columns end and the dot that represents the levelized cost of production, that's the carbon price. And you can see that that cost is much lower for the decarbonized pathways. But that difference is not enough to completely close the gap. We conducted a sensitivity analysis. Those are represented by the error bars. And it can be seen that for most pathways, under an optimistic combination of, let's say, high carbon prices, high metallurgical coal prices, and low electricity prices, some pathways can beat the basic oxygen, unabated basic oxygen steelmaking, but it's not generally the case. This chart, however, does not tell the full story because these are levelized costs over the lifetime of a product, of a site. And the thing is that these costs will change over time. There is an increasing pressure on CO2 prices. There is the expectation that hydrogen prices will also come down with time as more electrolyzer capacity is deployed, and there will be learning rates. So we have also modeled how the break-even price for steel will be changing over time. To do this, we took into account an annualized capital cost that remains constant over time. And on top of that, we added all the variable costs and some of the fixed costs that we are also assuming constant over time, like labor or maintenance. But the costs that are variable here are mainly the energy and feedstock prices. What this tells us is that after a general decline in break-even steel prices for most pathways in the coming years, that is aligned with the return of European energy prices to pre-COVID values, at least partly. After that, there is a strong increase in production costs, mainly explained by the increase in effective carbon prices. And it's important here to define what we mean by effective carbon prices. It's not just the price of EU ETS allowances, but it also reflects the fact that the free allocations of those allowances that currently the steel industry, primary steel producers receive around 80% of their allowances for free, those will be phased out as part of the carbon border adjustment mechanism in the EU. So you can see that in dark green we have unabated basic oxygen steelmaking. The price increases the cost increases significantly over time, whereas the production cost for the hydrogen direct reduction pathways tends to decrease because of the low impact that carbon prices have on them and the reduction in hydrogen prices. So we can see that the picture that we have today and the picture that we have in the 2040s or even in the 2030s is very, very different. And here we are still not reflecting the fact that there may be added benefits or there may be green premium. This is purely production costs. So we've talked about production costs. We will now move on to decarbonization, the decarbonization aspect. It's not only the cheapest pathway, the one that will be allowed to compete in a future economy. It's also the ones that meet government commitments and align with a net zero economy. So what you can see on the left-hand side is how the break-even carbon price, that's the carbon price that is required so that different pathways can achieve a cost parity with unabated basic oxygen steelmaking. So you can see how those break-even carbon prices evolve over time between 2025 and 2050, and also how the GHG abatement evolves over time. For all of our modeling, we've considered the use of grid electricity, and we know that grid electricity is decarbonizing in Europe and will continue to decarbonize. Particularly for those pathways that are very electricity intensive, there is a strong, a very strong dependency on the GHG profile of those pathways with the GHG, with the CO2 intensity of the grid. So you can see how hydrogen pathways, like here HDRI with electric arc furnace, how it moves towards the right and it moves downwards as the break-even carbon price reduces and as the emissions abatement increases over time. We can see that some of the decarbonization pathways, for example, retrofitting a blast furnace with CCS, can already shows a relatively attractive break-even carbon price that is roughly in line with expected carbon prices in the EU post 2030 with the effective carbon price. But however, they only lead to about 50% GHG emissions reductions. And that may not be sufficient to continue operating in a net zero future. Other pathways like hydrogen direct reduction with electric arc furnace show a higher break-even carbon price, but they allow to move into that deep emissions reduction zone and may make them more attractive from a commercial perspective. After completing that analysis, we did a full LCA modeling of each of these 9 pathways. And in this full LCA modeling, we considered not just Scope 1 and Scope 2 emissions, but also the emissions from associated with all material and energy inputs to the system. We consider the fossil global warming potential, as well as the biogenic global warming potential, and other LCA impact categories like fossil resource use and metals and minerals resource use, where we found that for basic oxygen steelmaking to be compatible with deep emissions reduction, as you can see in the third row in this table, capturing CO2 just from your blast furnace, even if it has a top gas recycling modification, that won't be enough to deliver deep emissions reduction. So addressing emission sources from other point source emissions in your steel mill, like the sinter plant, like the coke plant, or I don't know, the lime kiln, will also be necessary. It also reveals that even with the most aggressive decarbonization pathways, the residual emissions, the ones that you can see on the fossil global warming potential column, are still very high. So dealing with all those residual direct emissions and indirect emissions, and that means emissions from the captive lime kiln, but also emissions from electricity, emissions from hydrogen procurement, the treatment of waste, all those will be essential to drive down the total global warming potential of crude steel production. Working just on your direct emissions is not enough, and more is needed. What you can also see here is that, interestingly, for the direct reduction pathway, it's not just hydrogen-based direct reduction that results attractive from a GHG emissions perspective. Natural gas-based direct reduction, when retrofitted with a carbon capture plant, can lead to relatively low emissions reductions. And that is because emissions tend to be more concentrated in a single source of emissions, and that's the natural gas reformer for the direct reduction plant, and they are not as diffuse as in the basic oxygen steelmaking process. However, there remain very significant residual emissions that may be more challenging to deal with, like the upstream methane emissions. We've also modeled how this changed over time, because as I was saying, all of our analysis was considering grid electricity, and we know that grid electricity is decarbonizing. What we can see when we compare the picture between the 2020s and the grid intensity, the current grid intensity, and the expected grid intensity in 2050, where we are assuming that the grid is completely decarbonized and zero carbon electricity is procured, is that there is a very strong shift in a very strong decrease in those emissions for most pathways. You can see that that is particularly the case for the hydrogen hydrogen pathways, the red and orange ones in this chart, because they are very electric intensive, not just to operate the electric arc furnace, but also to produce hydrogen. And you can see that by 2050, those three direct reduction pathways, the two hydrogen ones and the one with natural gas, but using CCS, reduce their emissions by quite a lot. Residual emissions are still significant and something that need to be dealt with, and that includes the procurement of lime, the procurement of pellets, and other feedstocks to the process. That for our modeling, we consider that they continue to have current emissions intensity. Great. So that's those are the results in terms of cost and GHG emissions. The next step in our study was to consider what the requirements on the supporting infrastructure would be. Current steel production evolves around access to coal mines, access to iron ore. So the locations of current steel mills are not necessarily the locations that grant access to the resources and energy sources and feedstocks that are needed in a decarbonized steel production future. For example, if you need access to hydrogen, well, the place where steel mills sit today is not necessarily the place where they can get access to that cheap hydrogen. The same for access to a CO2 transport and storage network. So we looked at different feedstocks and new supply chains that need to be developed. And we found that in the case of the CO2 transport and storage network, this is a great challenge for most European steel mills. We looked at the EU 27 countries, the 27 countries that are part of the European Union. And out of the 29 integrated steel mills, 19 are more than 300 kilometers away from announced CCS projects. So it is quite challenging for them to be part of a CCS hub or cluster. In the case of hydrogen, if all of the 29 sites transition to hydrogen-based direct reduction of iron, not saying that that will be the case, but it's a scenario of maximum demand, they would claim up to 50% of the growth in hydrogen supply that is envisioned under the Repower EU plan. And that means that they will face lots of competitions from other sectors like the production of synthetic fuels or low carbon chemicals. There are also issues around proximity to transmission pipelines, and that may make this challenging unless the steel mills develop their own hydrogen supply, as is currently the case in one of the projects being developed in northern Sweden, where that project is also going for very big, very large scale. I think it's 900 megawatt electrolyzer capacity. In terms of renewable electricity, it's also huge demand. It represents an increase of 37% of European industrial electricity use if all of these 29 integrated steel mills move towards hydrogen DRI. If instead they choose to go towards the biomass or biofuel routes, it is a huge increase in the need for that resource. There is potential surplus, technical surplus of sustainable biomass and residual forestry and agricultural biomass, but it will face competition with other sectors, and it will also need the development of new supply chains. We briefly touched on the challenges around the DR grade pellet supply earlier on when we discussed that additional pathway we modeled that takes into account the use of BF grade pellets. But here, I just wanted to point out that the demand for DR grade pellets in Europe and elsewhere, because there are also many projects elsewhere, could grow to a volume that is 3 times as large as the current global DR grade seaborne market. So that requires a huge growth in DR grade pellet capacity. So it requires very early on work with the large pellet suppliers. It could also be addressed via some kind of vertical integration, that there is evidence of that already happening, where some of the steel producers are going upstream in their supply chain to get secure access to that. And there is also evidence of the other thing happening, where some of the miners are moving downstream, where they say, hey, I won't just produce the DR grade pellets, I will also produce the direct reduced iron, and then I can sell that DRI or hot briquetted iron. That's another form of DRI. I can sell that to the steel producers. Brilliant. So we talked earlier on that there would be an increase in production costs. The increase in production costs could potentially be passed on to consumers. Well, it would need to be passed on to consumers, otherwise the steel producers would go bust. Before we talk a bit about green premium, it's important to say what we mean by green premium, right? And it is a term that is quite ill-defined, and different people refer to it in different ways. Here we are talking about green premium as the additional price above that paid for the equivalent conventional substitute. What does that mean? That it does not represent the production cost differential. That's a cost premium. We are saying what the market is willing to pay compared to what they currently pay for the unabated commodity. This means that the extent to which the green premium will materialize doesn't only depend on what the production costs are, but also on the supply and demand dynamics, and mostly those supply and demand dynamics, and on the willingness to pay from the customers, which depends on the value they attach to that reduced GHG footprint. What is clear, whilst there is no clear answer about what that green premium will be over time and how it will evolve, what is increasingly clear is that the green premium will have a temporary effect. As supply ramps up in the 2040s, and also production costs for the unabated steel increase because of pressures on carbon prices. There is an expectation that the green premium will level off over time. So there is a clear first mover advantage, where steel producers that start offering this very low emissions steel can claim access to that green premium. Being able to claim that premium also depends on the kind of customers. There are sectors that purchase very high volumes of steel, that face higher customer pressure to decarbonize, and that have concentrated markets. So they are buying directly from steel producers instead of being several steps removed in the supply chain. So those sectors are the ones that are better positioned to lead the way, showing demand signals, paying that green premium. There are other sectors that just buy on the spot market and just pay for the commodity price. So for those, it's harder to absorb the green premium. As I mentioned before, estimating the green premium requires some supply-demand modeling and balance. What we did instead was to do a first principles exercise, where we estimate what may be the customer willingness to pay, depending on what's the value they attach to GHG emissions reduction. And that value that they attach to emissions reductions can be estimated based on their internal carbon pricing or the shadow carbon price. That shadow carbon price represents what's the value that they give to each ton of CO2 that is abated, and we reflected this in their purchasing options. So we moved back from the shadow carbon price to the GHG intensity of unabated steel production and on the price of that commodity to calculate what the green premium would be. And we found that for a shadow carbon price of around 100 euros per ton of CO2, that green premium would be around 30%. And for if the shadow carbon price increases to, let's say, 150 euros per ton of CO2, that still looks like something that is feasible and is in line with what several corporates have disclosed under the Carbon Disclosure Project. The green premium could increase to 45%. These premia of 30%, 45% are quite attractive. In some regions, they can make decarbonized pathways like hydrogen-based direct reduction competitive with conventional basic oxygen steelmaking, but it's not the case for the specific region we modeled in our study in Northern Europe. So something else is required. It could be either that these customers pass the cost on to end users so they don't absorb the cost fully, or that additional policy support is required to allow steel producers to reduce their levelized production costs. So those are the results of our study. There are lots of open questions for steel industry stakeholders. There are some areas that we did not address as part of the study, but that are emerging and that we are working on as part of other projects, like extending the analysis to other pathways, to model other impact categories in the LCA, to consider the decarbonization of upstream and downstream processes, including the treatment of waste products, but also the sourcing of pellets or lime. There is a lot going on around the decoupling of steel and iron. I briefly mentioned how some miners are evaluating or are already going into the direct reduction business, where they intend to sell hot briquetted iron to European producers. And there are wider geopolitical factors that weigh in. They are around trade. So identifying the cost optimal locations to transition to HDRI is a big area of current focus. And finally, the two other aspects are around commercial arrangements and business models, and then what are the wider barriers and enablers in the transition. So those are the high-level findings of our report, some of the results. And we are now open to receive any questions that you may have.
Thanks, Ignacio, for a brilliant running down through the findings of this study, and Sylvian, of course, for contextualizing this study. This is a very thorough study which covers a broad spectrum of decarbonization options for clean steel production. And to add more, you did went through and discussed the supporting infrastructure that would support the decarbonization of clean steel pathways. And you also did dwell into green premium, which is a very important context when speaking about decarbonization of materials, in this case, steel. I would encourage the attendees audience to get engaged and post your questions on the chat, and we will endeavor to answer each and every question contingent on the time. But before we go through the Q&As, let me seize the opportunity to ask the first question. Ignacio, Regarding the oxyblast furnace, could you elaborate more on what method you use in production of oxygen, and was that particular component of oxygen production decarbonized as well?
Yeah, thank you. So for the oxyblast furnace, what we consider there is that the top gas from the blast furnace is recycled back to the back to the blast furnace. There is an intermediate step where before that top gas is recycled, the CO2 is extracted, and then when it is injected back to the blast furnace, that is injected together with hydrogen enrichment.
Thanks.
For that hydrogen, we consider the use of an air separation unit, so the use of electricity, and we assume also the use of grid electricity.
A very important question came through. I'm not sure whether you or Sylvia will take this. The person in question was asking, please tell me how hydrogen costs will make steel viable to make it green and clean. So it is about the cost of hydrogen. How do you see?
Yeah, that is a great question, and it's a key component it was a key component in our modeling. We actually considered 4 different hydrogen supply strategies. We looked at the potential of blue hydrogen, the potential of green hydrogen. We also looked at the potential of electrolytic grid hydrogen, so still electrolysis, but with grid electricity. The hydrogen supply strategy has a huge impact on the cost and on the CO2 profile. The cost that you could see that we were showing today that didn't show the huge range of possibilities. Those are in the report, but not in the presentation today. Those correspond to electrolytic hydrogen with grid electricity. Those align with a hydrogen cost of around 4 euros per kilogram, 5 euros per kilogram, if I'm not wrong, on a levelized basis, starting from something close to 5 and falling to cost below 4 euros per kilogram after 2050. There are some regions that may benefit from much lower hydrogen prices. Again, that we consider that that's not the case for Northern Europe, so that's why we went for those hydrogen prices that could be seen as higher than what some other pathways consider. It could also be seen as more realistic for Europe.
A number of questions are coming related to hydrogen as well. An attendee is asking that you did consider electrolytic hydrogen production for this study. And he was asking, well, what about hydrogen from natural gas with CCS or pyrolysis technologies? If you have considered those hydrogen production, and if not, what was the basis behind why you haven't considered those pathways for hydrogen production?
We considered hydrogen from natural gas with CCS. It's one of the model sensitivities. We did not consider pyrolysis technologies, in part because we were presenting a range of technologies. It was not the representative of the whole universe of possibilities, but also partly because of very large volumes of hydrogen that are required and current uncertainties about possibilities for scaling up to such a big scale for some pyrolysis technologies.
Another question on hydrogen as well. It says, is there a required size needed for hydrogen? I'm not sure what he meant by size. Is it generated on site, on demand, or did you assume surface or subsurface storage? So I think
great question.
Yeah.
So, well, I'm not sure I understand the first part of the question, but the second part. In terms of required size, we consider for the blast furnace, for the basic oxygen steelmaking routes, if I'm not wrong, 4 million tons per year steel production capacity, and hydrogen what is required for to be compatible with that production. So not small pilots, but full scale. For the direct reduction routes, I believe we consider 2 million tons per year or 1.5 million tons per year for the direct reduction plant, and hydrogen, the typical yields for a direct reduction plant. So something like 60 kilograms of hydrogen per ton of DRI, top of my head, but that may not be completely accurate. But it's required size matching demand. In terms of generation, we consider both on-site generation and on-demand generation. We did not consider the role and additional cost of storage. Those could increase the cost of hydrogen supply.
Yeah,
they were not included in the modeling.
Yeah, very well then. Another question is the cost of materials. I think you must have covered that into your green premium discussion. And another question, could you please elaborate on the options considering carbon capture?
Yeah, so there are many options being evaluated, and those are different for basic oxygen steelmaking and direct reduction. For basic oxygen steelmaking, one option that is receiving quite a lot of attention is that top gas recycling with CO2 separation. That only deals with emissions from the blast furnace. It doesn't deal with emissions from other point source, with other emission sources. So other options are dedicated carbon capture plants for, let's say, the coke oven, for the sinter plant, for the lime kiln. That would be another possibility. Yet another possibility is the fact that integrated steel mills typically reroute all the top gases from different units. So coke oven gas, blast furnace gas, and basic oxygen furnace gas, those get directed to a on-site cogeneration plant. So a possibility would be to have a post-combustion capture plant after the cogeneration plant that, in terms of technology, it wouldn't differ too much from a post-combustion capture plant for power generation. So in terms of technology maturity, has a higher maturity. It still doesn't lead with all the point source emissions because it wouldn't deal with the sinter plant or the lime kilns. Might see it's another possibility.
I think we will accommodate one more question, or at most two. Then we close. What cost range did you assume for CCS? Also, did you consider any specific type of capture technologies? Example, solvent-based or?
Yes, so for CCS, we did not consider a range of capture costs. Instead, what we considered was we did a modeling of the energy implications. We consider the use of post-combustion amine-based with advanced amines, so not MEA, but advanced amines with a heat duty, if I remember correctly, of 3 gigajoules per ton of CO2. But anyways, we modeled that energy requirements, and based on the energy cost, we calculated what were the capture costs. We added a CO2 transport and storage cost in line with what is seen in Northern Europe. So that capture cost, transport and storage cost, I don't remember right now top of my head, but it was definitely over 50 euros per ton of CO2.
Thanks, Ignacio. I think we will stop the questions now. There are still questions streaming through. You could kindly direct your questions to any of the authors, Ignacio, Sylvian, or IEAGHG. And I wish to mention that the Clean Steel report will be published soon and will be accessible on the IEAGHG's website. I would like to say a big thank you to Ignacio and Sylvian and the wider ERM team for a job well done on this study. And I would also like to share a final thought, if time permits, within the next few seconds. It's important to note that production costs tends to rise as decarbonization efforts increases. However, inaction today is not a cost-free option. as managing and reducing emissions becomes essential to business and procurement practices, and failing to decarbonize will likely result in future market share losses and declining revenues. Finally, as we move forward, the IEAGHG will continue to closely monitor developments on emerging and mature technologies in the decarbonisation space. We remain committed to fulfilling our primary mandate to our members, and we will steadfastly continue to advance CCS as a key solution in achieving a sustainable low carbon future. So thank you to the speakers, and thank you to all that have attended this webinar. Thanks to Tim Wilson, the IEAGHG Communications Manager, for coordinating this webinar, and enjoy the rest of your day. Bye.
Thank you. Bye.
Thanks.